Okay, moving on to Newton's laws of motions. After we studied last class what forces are and how to diagram them, now we're going to learn about Newton, the famous Isaac Newton, and his three laws of motion, and how to combine our knowledge of forces to explain why objects move. Okay, this diagram right here that we have, that animation, is of something called a Newton's cradle, and it's often used to demonstrate conservation of energy in collisions, but it's a great model for everything, including Newton's laws of motion, and pretty mesmerizing to see. We have it in the class. We'll hopefully see it in January. And the objectives for today's class is to look at how we accurately draw forces in real life, how we understand Newton's first law of inertia, and then understanding and applying Newton's second law of motion. So to begin with, all right, when we look at, for example, this Newton's cradle and trying to understand why it moves in the way it moves, we have to first be able to draw the forces acting on, for example, that ball. If I can draw all the forces, I will be able to explain where it moves. Okay, and physicists draw forces on bodies using something called free body diagrams. So a free body diagram is a diagram showing the magnitude and direction of all forces acting on a chosen body. Let's take a look at this first. So this is just a random object that's going to be sliding on the floor, and I've presented that to you. So if an object is sliding on the floor and moving in this direction, then all the forces acting on it can be drawn here. Here would be the force of gravity that should start from the center of that object going downwards. And that force of gravity is going to be equal and opposite to the normal force, which should be acting from the bottom of that surface. So this is the force of gravity. That would be the normal force. And if they're balanced, they're the equal-sized arrows, which means that they cancel out. All right. And whoever's pushing this box is applying a force in that direction, which would be opposed by the force of friction between the object and the surface. And for that object to be moving towards the right, the force that he's applying must be greater than the force of friction. So that would be all the forces acting on a sliding box. Okay, all four of those forces drawn. All right, and any physicist who would look at that would know that the object is accelerating towards the right. Here's another classic situation of a parachute falling in the sky. Okay, and if I'm going to draw all the forces acting on the parachute, first of all, the force of gravity is acting on this penguin going downwards. And in order to stop him from accelerating and falling downwards, the parachute is applying a drag force. And if that drag force is equal to the force of gravity, that parachute will fall with a constant velocity, hopefully slowly. All right, next object is of something hanging from the ceiling, like a light. Okay, in this system, the forces are balanced, and I have the force of gravity, and as we learned in last week's movies, that's the force of tension. And you can see that here, the force of the wire and the force of the earth. If it's not moving, that means that they're balanced. The force of tension and the force of gravity are equal to each other. And that's a free body diagram showing something that is in equilibrium, which we're going to learn about a little later. Okay, and then the last sliding force, just to show something a little bit more complicated, would be an object sliding down a ramp, okay, or a hill. Okay, so this object is sliding down the ramp. Let's see if we can label what these forces are: A, B, C, and D. Okay, so let's start with B. All right, so with B, that's going straight down, acting from the center of the object. That's going to be the force of gravity. Okay, and if the object is accelerating down the hill, what do you think D would be? Well, D is opposing the motion of acceleration, so that would be the force of friction. Okay, and what would C be? C is acting perpendicularly to that surface, right? What force acts perpendicular? It's the normal, it's the reaction force. So that is my normal force, my reaction force between the surface, okay, as a result of the force of gravity. But notice it doesn't go straight up because the surface is angled. So that force is going in that direction. The force of gravity is going in that direction. Because they are not opposing in the same direction, they actually work together to push that object down the hill. So I have the force of gravity pulling down. Okay, I have that normal force pushing at that angle. All right, And so if I would combine those forces on an object, okay, they would look something like this. That's my normal force. That's my force of gravity. And when they both work on an object, I can connect, and that's going to be my resultant force. Okay, so that's the resultant force where the normal force is pushing that way, the other one is pushing that way. You can imagine two ropes. The result is that they're going to create a force that pushes that object down the hill. So this would be my resultant force. Almost like what I can say is the applied force. It's the applied force, but it's a combination of the force of gravity and the surface pushing at an angle that creates that resultant force, or that applied force. And that force needs to be greater than the force of friction for it to accelerate downwards. Okay, so free body diagrams allow us to visualize all forces acting on objects to understand the final motion of objects. Okay, that's really, really important. Now, getting to the next stage, after drawing free body diagrams, we can then apply Newton's laws. Okay, so Newton's first law says that a body will stay at rest or in motion with constant velocity unless an unbalanced force is acted upon it. Okay, so what does that mean? If an object is traveling at constant velocity, it means that all the forces are balanced. All right. If an object is accelerating, the forces are unbalanced. All right. So an object has inertia. All objects have inertia. Okay. And we talked about that in the class before, that inertia is the tendency of a massive body to stay in a constant state of motion. Okay. It's the reason why it's really hard to push a heavy car with your hands. You need a lot of force to move it because that car has inertia. In order to change its state of motion, I have to change its inertia. And you can see this video of a car. Okay, so this Lego car that's smashing into a wall slowly, it has inertia. It's traveling with a constant velocity, and it has an inertia. In order to change that inertia, I have to apply a massive force, which this wall is applying. And the result of that is the smash up of the car. Okay, so and all those little pieces, we're changing their inertia. Okay, so a force is what changes an object's inertia. And more importantly, in order to change an object's inertia, you have to change the velocity of the object. Okay, so Newton's law states that objects want to resist that change. Okay, and the force is what causes that change. And a good primary example of this would be this little magic trick, pulling the tablecloth out from a table. The heavier these objects are on top of the tablecloth, the more inertia it has, right? So it's easy for me to slip. Oh, that guy did something completely different, all right? That's a little funny little magic trick, okay? But in the little diagram below, this guy's pulling the tablecloth out from underneath these bottles. These bottles have quite a lot of inertia. There's very low friction between the tablecloth and the bottles, okay? So it can't apply that great of a force, and they're able to easily slide that out. I dare you to try it, but not with anything breakable. And just remember, the heavier the object, the easier it will be to pull that out. And if you use a cloth that is more like silk, that has low friction, you'll be able to do this no problem. Just try to do it with something that's not going to break, okay? So again, that demonstrates that if an object has a lot of inertia, you have to apply a lot of force to be able to move it. Okay, the lighter the object, the less inertia it has. You might not be able to do this trick. Now, the second law of motion states that a net unbalanced force on our body of constant mass is proportional to the body's acceleration. Another way of saying this formula is this. This is the one I say FMA. F equals ma. All right. So if I have an unbalanced force acting on an object, that unbalanced force is going to cause acceleration of that object. So the net unbalanced force, okay, that net unbalanced force, if I can calculate that, is going to create acceleration. All right, so let's take a look at this diagram below. All right, if this dude is applying a force onto the side of that 10-kilogram object, and that force is greater than the force of friction, the object will accelerate in that direction, okay? It's not going to move up and down because the force of gravity is equal to the normal force, Okay, so they balanced out, so they're not moving in that direction. But if my applied force is greater than my force of friction, the object is going to accelerate in that direction. So let's put some numbers to this. Let's imagine that this person is applying 100 newtons of force. And just to simplify, I know you can calculate force of friction based on what I taught you before, but let's just say this is a 10 Newton force of friction. Okay, so how would I calculate the acceleration of that object? Okay, well, I have to find first the unbalanced force, the net force. And the net force would be 100 newtons minus 10 newtons is going to be equal to, that's my net force, okay, is equal to 10 kilograms times A. Now, how do I isolate A? Well, in order to isolate A, I got to move the 10 kilograms over. And I'm left with 90 newtons divided by 10 kilograms is equal to 9 meters per second squared. Okay, that's my answer. So that object will accelerate in that direction with 9 meters per second squared. And then I can ask you some kinematics equations after that. So let's take a look at some more examples of Newton's second law and work through them together. You can pause the video at any moment just to go through this on your own and then see the answer that I'm about to put up. All right, so pushing objects, just like I showed above, a student pushes a 100 kilogram box across a floor with a friction coefficient of 0.3 using 50 newtons of force. Calculate the resulting acceleration. Okay, so we have to break down this problem. This problem's asking me to calculate the acceleration of a box sliding across a floor that has friction. Okay, and the applied force is 50 newtons. Okay, so I better draw a diagram. So here, okay, that guy's pushing the box across the floor. I have the force of gravity. I have my normal force. I have a force of friction, but I don't know what value it is. Okay, so I do know force of friction is equal to Fn times mu. Okay, I probably need to use that to find the force of friction. And it said that the applied force is equal to 50 newtons. Okay, so we have that, and this is 100 kilograms. Okay, so that's my diagram. So what I need to do is in order to find the acceleration, I need to use this formula. So F net divided by the mass is equal to my acceleration. All right, so how do we go about doing that? Well, F net is going to be 50 newtons minus my frictional force, which is going to be Fn times mu divided by 100 kilograms. That's going to give me my acceleration. So how do I solve for Fn? Well, Fn is equal to my weight of the object, okay? So 50 newtons minus 100 kilograms times 9.81 meters per second squared, that's Fn, times 0.3 divided by 100 will give me my acceleration, okay? So if I just wanted to round up, this should be, okay, 100 times 9.81, that's 981 meters per second squared, or 981 newtons, times 0.3, oh, it's going to be like 300 newtons. So 50 newtons minus 300 newtons divided by 100, that object is going to be accelerating in a negative direction. That object actually isn't going to accelerate at all. Okay, this person isn't applying a great enough force to overcome the friction, so that object isn't going to move. In order for that object to move, okay, instead of 50 newtons, maybe he needs to apply 500 newtons. Okay, and then if it was 500 newtons, then you'd have something. So 500 newtons. So 500 newtons minus roughly around 300 newtons would give you 200 newtons. That would give me an acceleration of around 2 meters per second squared. Okay, so important to understand that in order to get over friction, I have to apply a minimum amount of force to overcome that friction. Okay, in this case, the friction would have been too great. So 500 newtons would have been enough. Okay, so that probably should have read 500 newtons. So 500 newtons minus 300 over 100 will give me around 2 meters per second squared. Okay, the next problem is an elevator problem where it's lifting an elevator with 10,000 newtons of force. Okay, calculate the acceleration of the elevator when the mass of the elevator and occupants is 800 kilograms. Okay, so I've got to draw the diagram. All right, that's my elevator. These are the cables pushing up. Okay, so that's going to be my applied force. And then this is going to be the force of gravity. Now, hopefully, my applied force is greater than the force of gravity to accelerate the object up. Okay, so I'm going to apply F net is equal to ma. And then we have 10,000 newtons minus the force of gravity, because my applied force is working against the force of gravity, which is going to be 800 kilograms times 9.81 meters per second squared, okay, because this is my applied force minus the force of gravity, is going to be equal to 800 kilograms, that's the mass of the elevator, okay, times acceleration. So how do I get rid of that? Okay, so one thing I can always do, that like I did in this problem, is I'm just going to round that up to 10 to get me an estimate. So 800 times 10 is 8,000. So that's 8,000. So 10,000 minus 8,000 is around 2,000 newtons. Divided by 800, okay, it should be around like 2.1 or 2.2 meters per second squared. Okay, I'm not putting that in my calculator, but I'd say it's like greater than 2 meters per second squared. So you should be able to solve that in your calculator. All right, so the elevator is going to accelerate upwards. And if you were on that elevator, you would feel a sinking feeling in your stomach. Okay, last problem here is the thrust problems. Okay, so if I have a rocket, okay, and the rocket has a thruster jet, okay, so it's thrust that's pushing up on the rocket. Okay, the rocket's 1,000 kilograms and it applies a thrust of 20,000 newtons upwards. Okay, what is the rocket working against? Well, the rocket is working against the force of gravity. Okay, so my net force is going to be equal to ma, and that net force is going to be the force of thrust minus the force of gravity, which is equal to ma. So the force of thrust is going to be 20,000 newtons minus, how do I calculate the force of gravity? It's going to be mass times gravity. So 10,000 kilograms times 9.81. No, that's not 10,000 kilograms. It's 1,000 kilograms times 9.81 meters per second squared is equal to ma. Okay, so 20,000 newtons minus 9,810 newtons is equal to 1,000 kilograms times 8. Okay, so that should be roughly 10 meters per second squared. Okay, and we'll stop there. The next video that I'm going to present to you is something about pulleys. Okay, so we're going to do a whole video dedicated to pulley systems because they're a great way of learning how to apply Newton's second law of motion. All right,